Our today's speaker is Dmitry Molchanov, who will give a talk about the paper which has been just rejected from ICML and variance networks, or the cases when propagating expectation doesn't meet your expectations.
Hi everyone. Alright, so let me tell you about our unbelievable results. Unbelievable as in the sense that the reviewer didn't believe they're actually correct. So it is still a work in progress and we don't understand a lot of about what is going on, but I'll try to share our observations and our intuition about what is happening. So all of you, so everyone uses some kind of stochasticity when training neural networks. It may be something simple like binary dropout or Bayes normalization, or more advanced techniques like Bayesian neural networks. And so during training, they just inject some kind of noise. And during testing, we have several options. One of them is to just take this computational graph, take the random nodes in this graph and replace them with their expectations. I would call this mean propagation. The second option is to average the output of the computational graph over all the random variables, which is ensembling. And there are also some more advanced techniques that try to approximate the output of the ensemble. For example, you can try to distill the predictions, or you can use some approximation techniques like fast dropout, etc. But these techniques are pretty exotic, and usually you just take the expectation, plug it in your neural network, and be happy with the results. So, what does the noise during training mean? Is it just some kind of regularization, or can we actually learn some informative posterior using it? So consider, for example, binary dropout. We have one dropout rate per layer. The noise does not depend on data or on the data set at all. And we can't, so we do not learn its parameters. So it is non-informative. As for a bit more complex case, fully factorized Gaussian posterior, so where you just try to model the weights of a neural network as a Gaussian distribution, you actually usually learn the expectation of the weights and some small variance surrounding this expectation. And actually, you can do a fun experiment. You can permute all the sigmas in a single layer, and you obtain the same results. It means that the sigmas are not really very informative. But it captures some kind of uncertainty in the weights, whatever that means, and acts as a regularizer. But can we do it in a more informative way? So we can try to fit more complex posteriors. For example, use multiplicative normalizing flows. But come on, have you ever seen anything deeper than a linear 5 using multiplicative normalizing flow? I haven't. Not yet, at least. So can we explicitly learn some informative noise for batch ensembling? So I'll tell you about variance networks. I want to try to do it. So we consider a fully factorized Gaussian distribution over the weights. For now, just forget about all the Bayesian stuff. We just put some noise over the weights of a neural network. So we model our weights like this. We want to learn the expectation of the weights and the variance. And how to learn informative variance here? Well, we can just drop the μ's completely and use this distribution. Will this work? So yes, it works. Basically similar to ordinary neural networks, surprisingly. Even though it seems strange at the first glance. So the expectation of the weights is always 0. The expectation of the output of a layer, which is a linear operation, is also 0 for any object. But still the network learns some information and gives about state-of-the-art performance.
Does it work for linear models?
It depends. It is a bit tricky. So yes, you can learn. Yeah.
What about the mean after the nonlinearity?
Yeah, that's
Is it 0, 2
No.
or not?
No, that's the point. So okay, so let's look at the distribution of the activations before nonlinearity. So we have some fully connected layer, for example, with input x, weight matrix W, and output y. And the weights are modeled as a fully factorized Gaussian distribution. It means that the output y also follows a fully factorized Gaussian distribution with zero mean and with this kind of variance, because it is just a weighted sum of Gaussian random variables. Okay? And also this procedure is known as the local representation trick. If you try to train a Bayesian neural network, you would do it like this. And then to sample the activations, you just take this term and multiply it by some Gaussian, standard Gaussian noise. And you can see that this distribution is symmetric. The sign is plus or minus 1 with equal probability. The expectation is 0. But if you apply a nonlinearity, for example RLU, it breaks this symmetry. And that's why it works. So you can see an examples of distributions for y. So this is, for example, activations of one neuron, the orange plot, and the blue plot is the activations of another neuron. And after we apply a value, these distributions shift like this. So a value of a zero-center Gaussian is a mixture of a half normal distribution, something like this, and a delta peak at 0. Because half of the mass is less than 0, it becomes 0 after value, and everything else remains the same. And now the expectation of such term is actually does depend on the input. You can calculate it, but it is not relevant for now. And you can see that you can distinguish, for example, if it is one neuron and two objects that are passing from this through this neuron, you can actually distinguish between these two distributions. If the sample is like larger than 1, then probably it is the orange class, and if it is less than 1, then probably it is the blue class. And an important thing to note here is that you can use an absolute value as a nonlinearity. It would work approximately the same because, as you can see, absolute value of such Gaussian random variable is just a half normal distribution without this delta peak at 0. So you can see it as value as a binary dropout applied over an absolute value nonlinearity. Okay? And this is just some extra noise. We probably don't need it because we already have a very noisy posterior. So we can just use the absolute value nonlinearity and training will be more stable. Alright, so what can we learn from this? So there is no mystery. The nonlinearity breaks the symmetry of this distribution, and now the distributions are easy to distinguish. But the information is now stored not in the actual value of the activation, but in its magnitude.
Why do you tell about the distinguishedness of distributions? The initial distributions were also distinguishable before nonlinearity as well.
Yeah, okay.
So this is just one point.
Yeah, okay. Okay. And if you add biases, this will become even more expressive because these distributions will also shift somehow. Alright, and yes.
So if we use some symmetric nonlinearity, the model becomes completely broken. Or not?
Actually, it is not completely true. For example, you can use a sigmoid nonlinearity or hyperbolic tangents, which is an antisymmetric function. So typing that looks like this. And if your variances are very large, for example, you have an activation that follows like this distribution, then it would become -1 or +1 with probabilities 0.5 and 0.5. Yeah, it does not depend on data. However, if the variances are pretty small, so the distributions are zero-centered but look like this, then we can still distinguish between this distribution, and this distribution.
But the layer becomes in fact linear in this case.
Not linear because like this function here is not linear. It is close to a linear function, but it is not exactly linear. I would argue that an absolute value or a value is more linear than a sigmoid. Yeah. So it is very hard to learn the model with such nonlinearity, but it is possible. Alright, so what if we try to use other distributions other than Gaussian? Well, we can try to use any symmetric distribution. For example, a symmetric binary dropout, which is a Bernoulli random variable, which takes value -1 and +1 with probability 1/2, and multiply it by the weights sigma in this case. Or we can try to sample epsilon from a symmetric uniform distribution and also multiply it by the weights. All these procedures work. They work a bit worse because you can't do the local reparameterization trick here. At least we didn't try to do it because you would need to do it approximately. But it still works.
But you didn't try to practice, yeah?
We did.
You did.
Yeah, we did try it in practice on small models, but it works.
But without
I saw a paper on IQ which did the same thing with like something like Bernoulli distribution and then central theorem, central limit theorem, and then use a vector as usual.
Oh yeah.
But it's the same as the justification of Gaussian dropout.
It is similar.
Yes.
This topic is covered really well in the fast dropout paper. Alright, so this is a fun toy example, but does this model actually arise in more sensible models? Actually yes, and I want to show that variational dropout is also a variance network. So recall variational dropout, you have a fully factorized Gaussian posterior with such parameterization and a log uniform prior distribution. You train this model by optimizing the evidence lower bound. You have the data term, the KL term, which looks like this with respect to the variation parameter alpha. And this KL term favors large dropout alpha. And let's consider the simple case of variational dropout when you have only one dropout rate alpha per each layer. And in the original paper, in this case, authors had to clip the value of alpha. They restricted it to be less than 1. Why they did that? Well, because they probably saw a picture that looks like this. During some point in time, for example, at 40, the accuracy of the deterministic procedure just drops to a random guess. And it happens because alpha grow out of control. For example, here alpha is greater than 10 to the power of 5. But still, the stochastic and the ensemble procedure work exactly the same. They do not drop at all. All right? And the cool thing is that after that point, when alphas are very large, we can actually discard the expectations and only sample the weights using the variance of the weight and assume that the expectation is 0. And why we can do that? Well, if you try to calculate the distance between these two distributions, for example, divergence, you can see that it is equal to 1 over 2 alpha, and it goes to 0 as alpha increases. Okay, so these two distributions, when alpha is very large, are basically the same. And so after such approximation, we do not change the prediction of the network. And we obtain a pure variance network because we don't have the expectations and have some variances for each weight. And as we will see later, this trick only works when there is 1 alpha per layer or 1 alpha per neuron. If you use 1 alpha per weight, as in sparse variational dropout, you obtain a sparse solution with no phase transition. So, by phase transition, I mean this accuracy drop. And we will see why it works that way. And so when you train a neural network using variational dropout, at first you start training as a usual low variance network, something with low dropout rates, and then smoothly transition to variance only network. Which makes the training pretty stable, and it usually works better than just trying to train variance only network from scratch. And now we can also notice that the original procedure, when we don't use any of the Bayesian stuff, we just sample the weights from the distribution. It is actually just variational, a special case of variational dropout, because the KL divergence between such approximate posterior distribution and the log uniform prior is constant. Therefore, you can just discard it from the evidence lower bound and optimize the expected, there should be a logarithm, expected log likelihood, as you do in usual neural networks. And it is pretty unexpected because the log uniform prior was, in some sense, the most strong prior known to us that led to an overly regularized model. But here, in this objective, we see no regularization at all.
Well, regularization is contained in our variational distribution in Q.
Yes.
Why the log uniform prior is the most powerful prior?
It is just a hand wavy way to see it.
What do you mean by
I'm
no
not sure.
regularization?
In the objective, you don't see the regulation term. It is just log likelihood.
Shouldn't there be a logarithm?
Yeah. It's a typo. Right, and you can try to consider different parameterization of variational dropout. So you can take 1 alpha per layer, you can take 1 alpha per neuron, you can take 1 alpha per weight, or you can use additive noise, like here, and try to train it. And what you see is that after training, the evidence lower bound in the layer-wise parameterization and in the neuron-wise parameterization is much better, by the several orders of magnitude better than the weight-wise or additive parameterization. And it seems pretty strange because these two parameterizations are very simple posteriors, which are much less flexible than these two parameterizations. There is about twice as less parameters. But still, somehow it happens that the more flexible posteriors yield a worse elbow, evidence lower bound, and maybe a worse approximation to the two posterior, as if we use the evidence lower bound as a proxy metric. And as for the accuracy, the ensembling accuracy is the same for all 4 models. But the deterministic accuracy, so here you see the full phase transition, which is random guess quality. And here you can see that the phase transition started, but has not completed fully. And what it means is that these two parameterizations somehow get stuck in a poor local optima if we consider the evidence for bound as our objective. So an intuitive way to see why it happens is to consider this objective and see that in all cases the data term goes to very low values, and almost any network can feed the training data perfectly, so that you achieve 100% train accuracy and very low cross entropy during training. But if you use a simple postulator, for example 1 alpha per layer, alpha goes to very high values, the KL divergence is exactly 0. But in sparse variational dropout,
Well, it's not 0, it's some constant.
yes, it is some constant here. Which, so you can, yes. Look here, so we use the KL divergence using an additive constant, so that when alpha goes to infinity, it is equal to 0. Right? And by no way, by choosing another value of alpha, we can go below this constant. Okay, and so in variance network, this term is 0 up to a constant. This term is very low. And in sparse variational dropout, this term is about the same, but this term is huge, because a lot of alphas go to infinity. They do not contribute to the whole KL divergence, but there are some alphas that are stuck in small values. And so then why does it happen? Why does sparse variational dropout get stuck in a poor local minima? Well, it turns out that we, by chance, specifically designed our optimization procedure to do it, for it to get stuck in a sparse solution. So if you use the additive parameterization, you can now write that alpha is equal to sigma squared over mu squared, because the postulator was Gaussian mu alpha mu squared, mu sigma squared, right? So alpha is sigma squared over mu squared, and now the KL divergence, which was a function of alpha, it now is a function of sigma squared over mu squared. Yeah? And now we can plot this regularizer term for different values of sigma with respect to mu, and the same for different values of mu with respect to sigma. And when we train sparse variational dropout, we initialize all variances with very small values. For example, logarithm of sigma is equal to -10, and you can see what happens to the KL divergence with respect to mu. It is very sharp. It has a very sharp peak at 0. And when you increase sigma, for example, logarithm sigma means -5, it is not as sharp. If you increase it even further, it is completely flat. Okay, and it means that in order to increase alpha, it is much easier for mu to go to 0 than it is for sigma to grow. And that is why we just take these mu's and send them to 0, while alpha goes to infinity. Okay, and if you consider the KL divergence as a function of sigma with mu fixed, you can see that the gradient of the KL with respect to log sigma is always greater than -1 and less than 0. It is bounded, and the gradient over mu is very huge. So that is why logarithm of sigma slowly creeps to plus infinity, but it is too slow, and mu's go to 0 much faster in practice. Does this make sense?
But it is huge only in a small range, near 0.
Which values do you use when you initialize the weights of neural network? You initialize them using like something like Xavier normal or Lorentz uniform. They lie out here. They are very, very small in the beginning.
I have a question, but I can't express it. No, it's not about the language. So is the problem with this KL term in sparse VD with the neurons which are sparse but with not so huge alphas, or with the neurons which are not sparse, or with the weights, not
The problem is with the weights that are not sparse.
But like,
If
I
a
think
weight
this explanation is about the neurons which are sparse, but they have very small mu, but not that large sigma.
Yes, they have very small mu,
But they
not
are
that
still
large sigma,
sparse.
and yes, and if so, you can see that the alpha is sigma squared or mu squared. If sigma is fixed and mu goes to 0, alpha goes to infinity.
So this is about the neurons which are sparse,
Yes.
like which you drop.
Yes,
And what about the neurons which are not sparse in
Okay.
the sparsity?
and the ones that are not sparse,
Not a problem? They are
They-
a problem too.
so they are the problem in the sense that they contribute to the KL divergence in the end of the training. Yes.
So like, there's still a problem. Your KL divergence still is not 0 in any way. If you not drop everything, then it's not 0.
Yes, but it seems that when the neural network is very, very sparse, then you can't afford for sigmas to be large. So you can't sparsify it even further, but you also can't grow sigma because it will hurt your predictions.
I'm not sure why is it like a bad local optimal, because like it's simply a connection between KL divergence and elbow. So it's like, okay, your KL divergence is. I don't understand why this is bad.
It is not bad from practical point of view. From practical point of view, it is very, very good. But if you look at the evidence lower bound, it is bad.
Do we really care about evidence lower bound?
Well,
Or why do we?
when we train a neural network, we try to solve an optimization problem, and ideally we would like to solve it very well. And if a very good value of the objective corresponds to a bad module, well, the objective is bad. We can try to introduce some hacks to try to
It simply
go
means
to a
that
better.
we do not want to optimize elbow actually. We want to optimize the accuracy. So
Yeah.
okay.
So
The optimization of elbow doesn't lead to the degradation of performance.
It doesn't lead to the improvement of performance. So why do we care? I don't really understand. Like I understand all the points from the next slide, but I don't understand. Okay, and what?
Well, here the motivation of this slide is that the result is somewhat paradoxical, because we have a more flexible variation approximation family, and we get worse results in terms of Bayesian inference. We should get better and better results if we use richer and richer families. And our Bayesian variational inference is worse.
Okay, the problem is the optimization.
Yes.
Yes.
Okay.
And also the problem is that if we had a very good optimizer that would solve this optimization problem very well, and we would feed it the module of variational dropout, we would obtain this solution, not a sparse neural network.
I mean, it will be sparse, no?
No, it won't be sparse. Why would it be sparse? So if the global option of this functional is not sparse, and we find it, well,
Oh, you mean the sparse neurons will be like have a huge sigma, and therefore alpha will be also.
no, alpha will be huge, but
And they will be sparse?
And mu will be equal to 0, sigma will be not equal to 0. But they will not be sparse, they will be variance only.
Oh
So-
my God.
Yeah. So there are two ways to see it. There are sparse muons and weights. So the weights where W normal approximately 0, yes, and you can just ij, and you can just set W and J to 0, and it does not hurt the performance of the module. In the second case, it is sparse.
And the mu is 0 and sigma is not 0. Yeah?
Right.
Yeah. And we cannot set W to 0 because this results in a random guess quality prediction. It is variance. And the elbow objective does not care if our weight is sparse or variance because the Kyle dividends term is the same and the data term is also the same. So if we want a sparse solution, we need to add some optimization hacks in order to converge to this local optimum. Okay? Okay, variation dropout is fine, but it has some kind of weird improper prior distribution. And maybe this effect is because this model is incorrectly posed. And actually there is a paper that states that variational dropout is not a good model and that the actual true posterior distribution in this case is non-existent. Well, we can try to consider some proper probabilistic models. For example, we can try to consider a student distribution. So the Kyle divergence. So we use students prior with the degree of freedom nu and a fully factorized Gaussian posterior, the same one as in the variance networks.
And what about other parameters, like mean and variance of students?
0 mean and
0 and 1, yes.
yeah,
Standard student,
standard
okay.
student, yes, with common. And you can calculate this Kyle divergence, not exactly, but so it should be an equal sign, but then you would substitute the expectation with a Monte Carlo estimate. So up to some kind of constant, which is this expression, which, as it can be shown, when mu goes to 0, this expression converges to the Kyle divergence between the fully factorized Gaussian and the log uniform. So this happens because log uniform distribution is actually a limit case of students T distribution for nu that is equal to 0. Okay? And if you consider students T prior with a very small degree of freedom, for example 10 to minus 16, which is basically very similar to log uniform prior, you obtain the same results. But the model is now correctly defined. And maybe a little bit more practical example is the automatic relevance determination prior from the relevance vector machine. So you can consider the fully factorized Gaussian prior distribution with the 0 mean and with variance sigma squared. Each weight has its own variance, prior variance, and you still have the same posterior distribution. And if you calculate, so you can calculate the Kyle divergence between this posterior and this prior, and then optimize it with respect to sigma. And find that the optimal Kyle divergence looks like this. If you want, I can derive it, but I'm not sure if this is relevant. Does
It's
okay, okay, and as you can see, so the KL divergence between the fully factorized Gaussian and the log uniform prior, which is blue, and the KL divergence between fully factorized Gaussian and the optimal RD prior, which is yellow, they look basically the same. And the properties of the model is also the same. For example, so firstly the performance is similar. You also obtain the phase transition, you obtain the same quality, you hopefully obtain the same sparsity if you train it as sparse variational dropout. And the KL divergence between the posterior and the prior distribution also only depends on alpha, which was the main justification for the log uniform prior in the variational dropout paper. So maybe the use of log uniform prior was not the best choice for the Bayesian extension of Gaussian dropout. Maybe this is the correct way to define variational dropout, variational Gaussian dropout. Alright, so now I will show you some uplifting results. I will show that the model somehow works. So here you can see the classification results on MNIST FR10, FR100 on different architectures, LINET 5, and about 16 layers of VGG-like network. So we trained it using dropout training, simple binary dropout, and using variance layers. And as we can see, the ensembling quality is almost the same for all models. Sometimes the variance performs a bit worse, sometimes a bit better, but the results are basically the same. But the deterministic quality is good for dropout network, but almost random guess for variance network. So this experiment shows that we are really able to learn these models up to the same level of accuracy as usual models. And this experiment is about the stability against adversarial attacks. So we compare variance networks against the simple deterministic network, which is the blue line. So on this plot, on the x-axis, you see the number of updates during the adversarial attack. So you can see it as the strength of the attack. And on the y-axis, you see the rate of successful attacks. So the closer the line is to the bottom, the better. Okay? And you see on the top there is a blue line, which is a simple deterministic network. After that comes a dropout network, then a deep ensemble, which is just an ensemble of, I think, 5 or 6 networks trained from different initial guesses. And only then comes the variance network and the variance ensemble. The variance ensemble is an ensemble of 5 or 6 variance networks. And as we can see, the variance networks are more stable to adversarial examples, while the accuracy is still the same. And these are some very, very fresh experiments in reinforcement learning. So Arseny, please check that I don't mess anything up. So we had 2 environments, a car spool where you have this car that needs to balance the stick. And on this plot, on the x-axis you see the number of episodes, and on the y-axis you see the average reward. And as you can see, the variance network starts rather slow, slower than a deterministic policy network, but at the end it learns a better policy, which gets high reward.
Yeah, it's very preliminary results. But I would mention that we kind of can perform better exploration if we use parameter noise instead of noise in action space. So it's kind of
Are there confidence intervals given
Yes.
Yeah.
As you can
for
see.
all three curves, right?
Yes, yes, yes. They are very, very small in this experiment, and in the next experiment they're larger. And here the task is, so you have this moving arm, and the task is to, for its end to cross this line.
What is PN policy?
PN is parameter noise,
Yeah.
which is basically some fully factorized Gaussian noise over the weights of.
Is it a
Without
noisy
any
nets
band
from
distribution.
behind?
Yeah. And here the picture is the same, whereas network starts out slowly, but in the end learns a better policy.
Am I right? The parameter noise is simply like your model, but not with variance networks, but with usual variance.
Yes.
Yeah, that's
Small-
the Gaussian part.
Yes, low variance, fully factorized Gaussian ensemble.
Okay.
Yeah. So now I will tell you about a simple heuristic that we use to see whether we can propagate the mean through the network. Yes.
You had a slide where you have accuracy on NIST. Don't you try the experiment like it was did? Don't you try the random perturbation of the class labels, and does your network fit on this data?
I think that we were able actually to fit the random label data, yes. So, but it just means that this model is expressive enough to fit such kind of data.
I like the fact that it doesn't work on random label. That's good. It works on random labels. That's good.
If you remember, absolutely the same model, variational dropout model, did not work on. Yeah, did
So
not
it
work
was
on.
about the fact that it finds this poor local optimum. Yes.
It is not poor local optimum actually. In this case.
It's like more generalizable, but like it's poor in the sense of the loss, like the loss function for training data, loss value.
So
It's poor.
in variational dropout, in sparse variational dropout, yes, we could learn two networks. First, that overfitted random labels, but was not sparse, and the second, that was sparse and did not fit the random labels. So in the first case,
And in the first case,
so you have a data term, data and fail, and this is good, and this is bad. In the first case, in the second case, this is bad and this is good.
what was the difference, like in the training?
Here we pre-train the model on random labels, and then fine-tune alpha or sigma using each
On
and the
the
starting point.
on the signal.
Yeah, on the sigmas. Okay, and elbow. So elbow 1, elbow 2. So in sparse variational dropout, in this case, the average lower bound was better than in this case, simply because the kernel dividends term has much higher magnitude than the data term. Okay, and so here you basically have this set to 0, this set to a very large number, this set to a not very large number, this set to 0. Yes, but in variance network, so this is sparse variational dropout. But in variance network, which is the same model, so that we can compare elbow. The data term is good, and the KL term is also good because it is just 0. So, yes, variational dropout actually can.
Not constant, zero.
No, constant, but if you consider the results with.
And are you sure that with variance
Yeah,
networks we can make data term good enough under the D0 setting with randomly permitted labels?
I don't remember
I'm not
right now.
sure.
I don't remember right now. So it was not 0, of course, but I think it was better than a random guess quality, much better. I'm not sure if we were able to obtain 100% accuracy here, but at least it was not random guess, and it was better than this L1. All right. So the mean propagation. So in all conventional neural networks where we use binary dropout, Bayes normalization, etc., we perform mean propagation, which is also known as weight scaling rule, which is also known as deterministic procedure. Everyone calls it Pauli bonds. And everything knew that it is not the correct way to do inference, but they just didn't see an example where this works poorly and just did it. And we want to try to understand why it fails and how to test when it fails. So we provide this kind of numerical criteria. So consider such distribution over the weights of a neural network. We want to, the weights, so one weight Wij, we want to test whether we can replace it with its expectation value. We can do it if and only if, if the deep neural network is almost linear on this interval. Okay? So basically you have the relevant value for this weight, which is marked with red lines here. And if the neural network is almost linear here, we can approximate it with linear function and propagate the expectation through the linear function. And if it is not linear, we approximate it with a linear function, and the approximation differs very much with the expectation, or with one sample. And to do that, we calculate the curvature of our neural network with respect, so at the point of our expectation mu. And to do that, we just compute the second derivative of the network with respect to the weight W. And then we compare it to the posterior variance. If the variance is small enough, then we can propagate the expectation. If the variance is too high for this curvature, then we cannot. Of course, it is just a heuristic because this criteria would fail for a ReLU network, because a ReLU network is a piecewise linear function. It would also fail if mu is a point of, how do you say perigib? So a point where the second derivative is 0, because it would tell you that the function is linear when it is not. But still, in practice, this works pretty well. So we denote this value as kappa ij and calculate it for each weight of the neural network. For example, during training. And here you can see the histogram of kappas in logarithmic scale during different epochs. So the blue epoch, the blue histogram corresponds to the network immediately before the phase transition, which is low variance and where the deterministic procedure works well, where we can perform mean propagation. The green histogram corresponds to a network immediately after the phase transition or during the phase transition, where the mean propagation fails, and the red histogram is the network that is fully trained. And as you can see, as soon as the several weights cross some line, some threshold, the deterministic procedure fails. And we can take this point, remember it, and then use it to determine if we can or cannot propagate the expectation. So here is another kind of plot. Here you have the epoch of training, and here you have the accuracy of two different of a deterministic procedure. So here it drops And on this axis, the green line, you can see the number of weights that cross this threshold in our criteria couple. So as soon as these weights arise, the accuracy drops. And finally, we can use this criterion to make the posterior distribution sparse again. So what happens in a variance network when you propagate the expectation? You take the variance weight 0 sigma j squared and you replace it with its expectation 0. It means that you zero out its variance. Yeah, essentially zero out. So if we can zero out a lot of sigmas, we can store sigma in a sparse matrix, and then, for example, compute local representation trick more efficiently, or store it more efficiently. And it turns out that for the same value of kappa 0, 1.5, we can remove, we can compress the posterior up to almost 100 times on linear 5 architecture. But unfortunately, this is also probably due to the poor local optimum, because this network was trained using variational dropout procedure. So at the beginning of training, the posterior looked like this. So you still have some mu's, some alphas. And probably this effect is due to the fact that during training, during the first several epochs, the term makes a lot of mu's go to 0 and makes them sparse. So we did not try to reproduce this result in a pure variance network when we trained it with zero-centered distribution from the beginning. But I would suspect that we would not be able to sparsify it as much without additional regularization of sigma. Because nothing in the objective.
Because there's no regression term.
Yeah.
No elbow in the setting.
Yeah. But at least in some cases we can do it. All right, and so there is still a lot of things that we don't quite understand about this model. For example, the first question is, are these ensembles actually really that diverse? Or maybe we learned something trivial? Well, let's see let's look at the variance layer followed by an absolute value nonlinearity. So here is the local representation trick for one neuron. And we can compute the output. We take the standard deviation from the local representation trick and multiply it by some half Gaussian distribution module of epsilon A. And it turns out that, so here is this distribution, the blue plot. Its expectation is about 0.8, its variance is about 0.3. And if we try to approximate it with such a Gaussian distribution, we obtain the same results as sampling from the true learned posterior distribution. So look what happened. We took a model with Gaussian dropout noise with alpha equal to infinity, but then we can reorganize the computational graph and replace the random variable, which was very noisy before, with a not very noisy Gaussian random variable with standard, with expectation 1 and standard deviation and variance alpha about 0.5, which is not that much. And we can try to do mean propagation here, and sometimes it works.
It works almost.
Yeah. So it is a very tricky thing because sometimes it works, sometimes it doesn't work. We are not completely sure yet, but yeah, sometimes it works. Even if you train the model with zero mean distribution over the weights. So why this happens? It happens because of this choice of nonlinearity. We learn a very broad distribution over the weights, but the nonlinearity breaks the symmetry and collapses it all to a very simple distribution. And an intriguing question is that, so, okay, we took a neural network with Gaussian dropout and set the Gaussian dropout rate alpha to infinity, which should probably be the most noisy network of them all. But it turns out that it is just equivalent to Gaussian dropout with alpha 0.5. And what is actually the largest possible noise that we can inject using Gaussian dropout? Well, it is not clear for now, and probably we will find out the answer
I
later.
don't understand. Why are they equivalent?
Because you can take the neural network after training and replace this term here by this distribution. It would work the same, absolutely the same.
I mean, if variance is infinity.
No, alpha is infinity. Multiplicative variance is infinity. It means
Alpha is infinity because your mu is 0.
yeah.
Okay. Why normal is 1 and 0.5 if you have 0.8 and 0.6?
You can normalize it by 0.8 to obtain alpha. I just did it so it would be more clear what is the signal to noise ratio of such solution. So basically this 0.5 is this variance, so this term squared over this term squared.
Oh.
And it is approximately 0.5, not exactly. So yeah, and also empirically we find that the uncertainty of variance network is not that good. We tried to compute out-of-domain uncertainty, and we tried to compute the uncertainty on toy regression tasks, and
But you had a plot about this. No?
which one?
These different samples and this. It was not about this stuff?
It was about adversarial examples. So variance networks are a bit more stable to adversarial examples, but the uncertainty is very poor and it is comparable to binary dropout. And if you use ReLU nonlinearities instead of absolute values, it works a bit better just because you add more noise using binary dropout, essentially. Pushing binary dropout over the absolute value nonlinearity. Okay, so another interesting thing. So we can plot not only the ensembling procedure and the deterministic procedure, we can plot a lot of different things. A lot of different ways to do inference during the test phase. So here are 4 plots. The deterministic accuracy, which is the blue line. Here it drops to random guess. The ensembling accuracy, which is also very good, always very good. So D0 is the module where we zero out the expectations. So we replace normal mu alpha mu squared with normal 0 alpha mu squared. Okay. And at first, of course, it is random guess quality, but somewhere near the phase transition, sigma starts to learn information, and then it works the same as the ensemble. And you also can calculate the accuracy when the sigmas are permuted. So here you can see that if you permute the variances in the layer, the accuracy does not change because it is a very low variance ensemble and all information is stored in the expectations. But after that, where sigmas are informative, if you permutate them, it results in a random guess quality. Okay, but what is interesting is this point here on the plot, because at this point, several procedures work approximately the same. for example, at this point, both the deterministic accuracy and the accuracy of the procedure that has zero mean and alpha mu squared as a variance is about 0.99, which is about as high as you can get with the linear 5. And it is very strange because you can you take one trained neural network with the posterior mu alpha mu squared. You can substitute it with Gaussian 0 alpha mu squared. You can substitute it with Gaussian mu 0, and it all work the same. How can it be?
So the
What happens?
You mean why, like, the expected result would be that these lines will be crossed not in the high level, but like
here. Yeah.
Maybe we should compare the distributions after the nonlinearity. And
Yeah,
it will
yeah.
be.
But it is not very clear how to do it. But we would like to figure that out. Okay, so we have variance networks, which was a very fun model to play with, which has a lot of counterintuitive properties. So it is the first practical example where the mean propagation drastically fails. Before that, everyone just put the mean into the neural network and it works perfectly, but not in this case.
Okay, this is the first. This is not the first case.
The first practical. One of the first.
There are some papers which do this, but like, okay, they have not such bad results in the deterministic case, but like much worse than in the undeterministic case.
Okay, and it turns out that probably if we train the neural network this way, although we thought that we put a lot of noise in there and that we train essentially a very rich ensemble, maybe it is not the case. And then the question still persists how to train a good Bayesian ensemble. And the greatest open question for us right now is, are variance network any good? Because without any good properties, it is hard to publish this model. So yeah, I think it is mostly all. So if you have any questions, yeah.
Could you please tell briefly about the reasons and maybe comments on the reasons of rejection?
The reasons of rejection? Okay,
What do
so
we need them?
so we had 4 reviewers. The first 2 of them
Maybe
were not
we
very
discuss
informative.
afterwards.
Okay, yeah.
I'm not sure that's
Yeah, yeah,
interesting for
okay.
everybody.
Okay.
But anyway, if we apply variance network to linear models,
Yeah.
what can we get?
We can, for example, fit linear regression. Which would not be exactly linear, but like we will have some x. So we can learn a model like this, for example. So you still need some kind of nonlinearity after the variance layer, even if it is just a linear model.
Okay. And if you have, I don't know, a couple of relevant features and all others are irrelevant, so in maximum likelihood solution, it would be some big values of weights for small
Yeah.
number of features, 0 values, almost 0
Yeah.
values for all others. So what equality would be obtained with variance network?
I suspect that it will be similar. So I suspect that the accuracy would be worse because, well, this model is more simple. So I would write it better this way: sigma times epsilon transpose x plus b. Yeah, where sigma is our positive weights and epsilon is random noise. And you can compare it to this model, w transpose x plus b. This model seems to be more flexible. This one.
Because
But why do you think that the quality would be similar?
the quality would be worse in this case.
Much worse, I guess.
It depends on the task.
If you have one big weight, any
No, I don't
any
think that,
other choice would deteriorate the quality.
I don't
very
think
hard.
that it is relevant if there are some irrelevant features or not. I don't think that it would affect the performance, but still, so if you consider all possible datasets, the average performance of this model would be worse, but there would be some tasks where this works just as well as this one. For example, I suspect that you can so I can't give examples right now, but I think I had something in mind.
But I think that this is one of the key things, that if you do not have a smooth transform of this model to the quality of just linear model, so there is the question, it means that this model is not correct. Because in the general case, you can't say which weights are really important, which are not, and which are good determined by the data, which are not determined by the data. And if your model can't adapt to this situation, it means that it is an incorrect model.
And I fail to see
Okay.
how you
Let's
came to this
discuss.
conclusion.
But like, can't you
Okay, so
understand which weight is more important by how high the variance is?
yeah, so
High the variance and the more
okay, so
important
look,
the
you
weight
can
is.
remove the biases and rewrite it like this. It will be module. So you can perform something like a local representation trick for this model. So it will be model epsilon and square root of sigma squared x squared, and voila, you just have something like a linear model over the quadratic features with positive weights.
But with randomly chosen epsilon.
But
You
do it,
put
for example,
expectation over epsilon,
Yeah.
and then you just here have 0.8.
So the expectation of epsilon is 0.
No, here is the absolute value.
0.8.
About 0.8, yes. Square root of 2 over pi. So this model is different from this model. I suspect that it is less flexible, but who knows. I think there are some cases where this model was better than this model. Yes.
Well, here we stick with kappa
Hmm?
in the 27th slide.
Which one?
We should
27,
take
okay.
maybe the absolute value of the second derivation, partial derivative.
Yes. What was in the experiments? The absolute value here?
Absolute value.
Okay, yes, absolute value.
And what is the smallest data set where you can find such effects like what phase transition? So maybe we can launch a small variance net on a toy dataset, like 100 objects, and we can watch how this forward propagation works on different objects. Some pictures maybe.
I think it is more about not the amount of data, but about the size of the network. And we found it very hard to reproduce the phase transition on smaller models. So basically, when you have a typical experiment from some Bayesian papers showing a regression task, so you feed y equals x squared curve, right, with some kind of amount of noise, with like 20 objects, or everyone uses one hidden layer neural network with one input x, one output y, and if we try to put variance layer here, it works very, very poorly. I don't know why right now, because I didn't spend much time at this experiment, but if you consider a deeper network, then you can easily feed a variance network to this data.
And because that you need nonlinearities to the variance networks to work.
Yes.
Maybe like you need more than one hidden layer to have more nonlinearities.
Maybe. But maybe I just couldn't fit this model very well because of the amount of noise. Yes.
And were the investigations to find or catch some connections between these phase transitions and behavior of the model in some kind of unstable points, maybe on the loss curves and in some street saddles, maybe?
So we didn't try to find anything.
Points, I mean.
So we didn't specifically look for these kind of things, but we didn't see anything strange during the training process as well. So it would be very interesting to see what happens during optimization. For example, like here. So what happens around this point?
Exists some.
But I don't know right now how to visualize this or calculate some statistics. What can we look at to understand what is going on? Because I think that the common consensus right now is that nobody really understands how deep learning works.
It's a huge frontier for us.
And this is just another open question. Yet another.
Any more questions? If not, then let us thank the speaker. So actually, probably this was our last seminar in this semester. So we will not have a seminar next week due to next deadlines. And in 2 weeks, instead of seminar, we will have some kind of mini workshop on Thursday on Faculty of Computer Sciences, where there will be 3 speakers who occasionally appear to be at the same place at the same time and kind of agreed to make talks about their research.